to the final special application for integrals, calculating volumes of solids formed by cross-sections. Our goal here, calculate the volume of a solid formed by stacking two-dimensional areas across a bounded region. And here's the problem that we'll set up for this application. A region R is bounded between a curve f of x and the x-axis. So here's a generic f of x curve, and I've labeled the region R. What we're going to do is in this region, build squares with one side perpendicular to the x-axis, covering the entire span of the region from the x-axis to this curve, and we're going to build those squares going upward, coming out of this two-dimensional picture and entering the third dimension. And what we're going to imagine is building up squares all the way across this region. 2D squares, 2D slices or cross sections of a 3D object. And what we'll think is, if we can add the area of every square, we will get a volume of the 3D solid, which sounds a lot like how we worked with washers and disks when talking about volumes of revolution. We're going to break this problem down into one small slice of the problem, figure out the calculation we need to do on that one small space, and then imagine doing that calculation an infinite number of times across our region. So how we'll attack this problem is we take one of these cross sections and draw it out in 2 dimensions. And one of the things we're still going to think about is this idea of our representative rectangle, the part of this square that actually came in contact with the region on our graph. And if we can define an area for this square, integration will be the tool that we can use to get the volume of our resulting solid. So think about the dimensions for the square. Squares we know have 4 congruent sides, and the side that's going to be easiest for us to define is the side that's within the region R. The distance between the x-axis and the curve would just be length f of x, which means every side of this square would be f of x. And the area of the square, which is always the side length squared, would equal our function value squared. And if we want to adjust this to a volume, we would need the formula for our area in terms of our function, in terms of our region, and we would need start and end points, which we've always called a and b. And our resulting volume would be the integral from a to b of the area of our square times dx. We're calling that when we do a cross section, it can't actually be 2D. It has to have a little depth to it. So we're actually more cutting out a miniature box than we are an actual square. And the depth of that box is going to be dx. That's what turns this into a volume. So to generalize the process for finding volumes built from cross sections, step 1, what is the area for the shape of the cross section? Step 2, express the area in terms of the distance across the chosen region, the one you're building the cross sections up from, the one that you're building the volume up from. And step 3, integrate that area from the start of region, what we usually call A, to the end, B. And so let's take a look at some common shapes that we can build up from bounded regions. There's our square, which, if we call our curve f of x and bind it between the function and the x-axis, building up a nice square from that, its key dimension would be f of x, and the area that's normally s squared would become f of x squared. And then we would simply integrate that from A to B in order to get a volume made up of these cross sections of squares. Another common one, particularly on the AP exam, is the isosceles right triangle, shown in 2 ways. With a leg on the region, so something like this, and being a triangle, we'd have 1/2 base times height, but the base and height in this case would both be the legs, which would be defined by f of x. And we'll get 1/2 f of x squared. We could also get the hypotenuse on the region. So taking our right triangle but having the right angle coming out of the page. And I won't go into the proof here, but this one turns out to be 1/4 f of x squared. Common shape number 3, a semicircle with a diameter built on the region. And that would look like this. Semicircle, built up, diameter stretching all the way across. The regular area for a semicircle would be pi times the radius squared divided by 2. But working off f of x being the diameter, the area for this cross section ends up being defined as pi over 8 times f of x squared. And finally, out of the most common shapes, building our cross sections by using an equilateral triangle. Getting one side of this triangle with 3 congruent sides built up. Area would still be our triangle area formula, but with all those sides being the same, if you work through a proof of this, defining one side to be f of x, we would end up with square root of 3/4 times f of x squared. This is just to highlight, if you think about how units work for areas, they're always squared units. The thing being squared in this case will always be the distance across the region, which I'm generically calling f of x, and the only thing that's changing for all these shapes is the constant we multiply that by. So a square has a constant 1. Isosceles right triangle, leg on the region 1/2, hypotenuse 1/4, building a semicircle with a diameter on the region, constants pi over 8, and the equilateral triangle, square root of 3/4. But it's all of these multiplied by the distance across the region squared. So you can memorize all those constants if you choose to, or get familiar with how to actually go about developing those formulas. But the biggest thing that we need to be able to define is the distance across our region. Once we have that, it's very straightforward. It's integrating from A to B, whatever area you have with respect to your axis. And that provides us with our volume of a solid built from cross sections of common 2D shapes. And that will do it for all the special integral applications that we will cover in this course. Make sure that you try practicing with all different types of shapes for these cross sections, getting yourself familiar with any situation that could possibly pop up, and thank you for watching.